in this section, we're going to take a look at how to solve an initial value problem using Laplace transforms. Okay. In the last couple of sections, we were laying a foundation for this. This is kind of our main goal in this whole chapter, is to solve differential equations using Laplace transforms, but not just differential equations, initial value problems. So let me quickly remind you what they are. We've dealt with these from day one of this class. So an initial value problem is a differential equation. Okay, it could be of any order, first order, second order, third order, a differential equation along with n initial condition. So if it's an nth order differential equation, we would need n initial conditions. So if you have first order, we need one initial condition. Second order, we need two initial conditions. That's what an initial value problem is. So the type of problems we can solve using Laplace transforms are initial value problems. Normally, we can solve an ODE directly, and then we'll end up with some constant of integration. If we had some initial condition, we could find that. But when we use Laplace transform to solve differential equation, it has to be an initial value problem. We have to have those initial conditions. So if we didn't have initial conditions here, we cannot use Laplace transforms. Okay, so just bear that in mind. All right, now before we do that, let me tell you why we need Laplace transforms, why go through all this trouble. Okay, so let me first lay some foundation down for you. First of all, Laplace transform, you'll notice soon when we solve some initial value problems, uses algebra. So Laplace transforms uses algebra to solve initial value problem. And the reason for that is because all the calculus that we would have needed to solve the initial value problem, we already took care of that in section 7.2, 7.3, and 7.4. So now we're just going to use straight up algebra to solve the initial value problem, and I'll explain that. The second thing that's really nice, so the reason why this is important, the first point, is because algebra is always easier to work with than calculus, and that's why we list that. The second reason why we need Laplace transforms is for some special forcing functions. If you recall, okay, so if you recall, we could have a differential equation like this: y double prime plus b times y prime plus c times y is equal to some forcing function, some g of x or g of t or whatever. Okay, now this forcing function could be discontinuous. That means it could have discontinuity in the middle, a piecewise discontinuity. It could be piecewise discontinuous is what I mean. Or it could be some special function like step function, which we'll talk about in the next section. It could also be some type of a periodic function. So Laplace transforms can handle a lot more different types of forcing functions. Okay, or these are called forcing functions, or external force, or input functions, whatever you want to call them. That's what they're called. Okay, so Laplace transforms will help us solve a lot of different varieties of differential equations than what we've been dealing with. Okay, so it is really powerful in that sense. The next thing is, if you recall, when we want to solve a typical initial value problem, we have something like this. We have, let's make one up. Okay, so let's say if you have y double prime plus 2y prime plus y is equal to 3, let's say e to the t minus t. And we have some initial conditions. We have y of 0 is equal to 1, and maybe y prime of 0 is equal to 0. Now, how would we have solved this problem using techniques from chapter 4? First of all, it's non-homogeneous. Okay, we have a forcing function. So we would have solved this problem what? First, we would have found the homogeneous solution, and then we would have found the non-homogeneous solution, correct? All right, so that's the first thing. This would be the first step. Actually, let me write them down. I'm not actually going to solve this. So what we would have done first is find the homogeneous solution. Okay, the next thing we would have done is we would find the non-homogeneous solution, and to do that we could have used variation of parameters and undetermined coefficient method. And just so you know, in this example it would be smart to use variation of parameters, just because the forcing function is going to get complicated because of the homogeneous solution is going to include the forcing functions. We'll have to keep multiplying this by t till we get to a point where it's no longer part of the homogeneous solution. Then once we get done with all of that, we would have to use the initial conditions and find the constants. So use initial conditions and find the constants. So that's a lot of work. We have to do three things. The cool thing with Laplace transform is you do solve this problem once, you do all of these three things together. In the end, you get one nice answer that'll include the constants, that'll include the non-homogeneous solution, that'll include the homogeneous solution. So you don't have to find three different things. You do solve it once and you get everything in one chunk. So that's really neat about Laplace transforms. Okay, now that we know why we need to use Laplace transforms, okay, let's take a look at how we solve initial value problems using Laplace transforms. Actually, let's not call it how. Solving initial value problems using Laplace transforms. Okay, so let me draw this picture. I've probably drawn this many times for you already, but let's do it one last time. Okay, so we have some initial value problem. Okay, it's in the t domain. I'll always use t's instead of x's going forward. It's in the t domain. Okay, and I want to solve this initial value problem. That's my goal. We want to solve this. Okay, now one way we've been doing this is, you know, in the previous chapters, okay, we've been doing this using calculus. That's what we did in chapters 2 and 4. Okay, we used calculus to solve it, and we came up with a solution. Okay, and this solution was y of t, the solution to the initial value problem, and this was still in the t domain. It was a solution in t. Okay, so this is the solution we came up with. So that's how we did this in chapters 2 with the first order ODE, and we did the same thing in chapter 4 with the second order ODE. And we also learned in chapter 4 that we can do that for the same thing for the third order, the fourth order, and so on. Okay, now what we want to do in this section, we want to take this initial value problem and transform it by taking the Laplace transform of it. Okay, so we're going to start up with a problem that's in the t domain, and we're going to transform it using Laplace transforms to a new problem. Okay, all right, now this problem is going to be in the s domain, and it's going to be a problem that involves function of y, s. Okay, so this is going to be a new problem. It's going to be an algebraic problem, first of all, not okay, and it's going to be in the s domain. Okay, so again, this initial value problem had to do with y of t, if you recall. Okay, because we were given function of t, y, which is a function of t. Okay, now we're going to transform it. We know how to do that. That's what we did in the last couple sections. Okay, how to take a function that was a function of t and change it to a function of s. Now what are we going to do? We're going to solve this. Okay, the only thing is now it's an algebraic problem, so it's easy to solve. Okay, so we're going to solve it and we're going to come up with a solution. Okay, so the solution is going to be big Y of s. This is in the s domain still. Okay, so we're going to solve using algebra this time. Okay, we're just going to solve for big Y. That's all we're going to do. Keep in mind, out here we start with something, we are working with Y, little y, and when we transform it, we are going to work with big Y. Okay, so keep that in mind. So we're going to isolate big Y, we get that, and then we're going to change it back to little y using inverse Laplace transforms, which is what you guys did in section 7.4. So this is basically 7.4, and this is 7.2 and 7.3 going this way. Okay, so that's what we are doing. So it's really cool because we are changing a calculus problem that has derivatives and everything. We're changing it to an algebraic problem. We're going to solve for big Y. That's all we have to do. It's an easy solve. It takes like 1 second to solve. And then we're going to change it back to little y of t. So we are avoiding this whole step of calculus. We're doing all algebra here. Okay, that's the reason why a lot of the engineers and other physicists and things like that, they prefer Laplace transforms because it avoids all the calculus and all the math, basically all the heavy math. Okay, now that we know what we're going to do, let's take a look at an example and see how it works. So let's say that I have y double prime minus 2y prime plus 2y is equal to e to the negative t. Okay, now this is a differential equation. Remember, to solve this equation using Laplace transforms, we need initial conditions. So we have y of 0 is equal to 0 and y prime of 0 is equal to 1. Okay, so this is what we have right now. We have an initial value problem. What are we going to do? Take a Laplace transform. So let's do that. So what I'm going to do is I'm going to take the Laplace transform on both sides. So I get Laplace transform of y double prime minus 2 times Laplace transform of y prime plus 2 times Laplace transform of y is equal to the Laplace transform of e to the negative t. Okay, now that we have that, if you recall from section 7.3, we know what the Laplace transform of y double prime is. Okay, now before I do that, let me just quickly remind you, just for notation purposes, when we take Laplace transform of little f of t, okay, we transform it, we end up with big F of s. So if we take the Laplace transform of little y of t, we're going to end up with big Y of s. So I'm going to use this notation now. So if you recall from section 7.3, y double prime is the same as s squared times big Y of s, I won't write that s, minus s times y of 0 minus y prime of 0. So this is the Laplace transform of y double prime. And again, that was covered in section 7.3. Minus, we have 2 times the Laplace transform of this, of y prime. Y prime was s times big Y minus y of 0. That was the Laplace transform of y prime. That again was covered in section 7.3. What is the Laplace transform of just y? Well, let's look at that. Laplace transform of just y is just big Y. So we just get 2 times big Y is equal to Laplace transform of e to the negative t. This was covered in section 7.2 is 1 over s plus 1. Okay. All right. So we have that because out here a is equal to negative 1. So that's how we get that. Now let's use the initial conditions that were given to us. That's why we need those initial conditions. We know that y of 0 is 0, so that's gone. We know that y prime of 0 is 1. Y of 0 is 0, so that's gone. So we get s squared big Y minus 1, that comes from here, okay, minus 2s big Y, I distributed this negative 2, plus 2 times big Y is equal to 1 over s plus 1. So what we've done so far is we performed the Laplace transform of the initial value problem that we started with. And that now we add this step. So we started with this, we started with this problem, did the transform, and now we are here. What are we going to do? We're going to solve for big Y. That's all we need to do. We want big Y by itself. That's all we need. So anything that has a big Y in it, we want to isolate that, move everything else to one side. So let's do that. So I get big Y. I get s squared minus 2s plus 2 is equal to 1 over s plus 1 plus 1. I move this 1 to the opposite side. Okay. Now what can we do? I can use common denominators and add these guys up. Okay, so we'll do that next, and so we get big Y times s squared plus 2s plus 2 is equal to s plus 2 over s plus 1. I just did common denominators, and then I'll divide by this. So I get big Y is s plus 2, this should be a 2, sorry, divided by s plus 1 times s squared plus 2s plus 2. So now we are right here. Okay, we solve for big Y, but we're not done there yet because I can do a little bit better. So this is where we're going to use what we did in section 7.4, which is partial fraction decomposition. We want to do the decomposition of this so we can do this step easily, going this last step. So I want to do the decomposition here so we can do this last step very quickly. Alright, so let's do that. So I'm going to do that on the side. So let me go ahead and call this 1 so I can come back to it later. Okay. Alright, so if you think about it, what do we have? We have s plus 2 divided by s plus 1 times. Now this cannot be factored, so you'll have to do completing the squares. So we get s plus 1 squared plus 1 is what you're going to end up with. Oops, it should be, did I miss a minus sign somewhere? Yep, this was a minus here, so let's change that. That becomes a minus. This becomes a minus. Okay. All right. How does this break to? These two are distinct, so we get a over s plus 1 plus this one. If you recall, because we do completing the squares, we want to write it as what? We want to write it as b times s minus 1 plus c times 1, whatever this one number is, over s minus 1 squared plus 1. Technically we have to write it this way: alpha plus c times beta over s minus alpha squared plus beta squared. I just split up the numerator, that's all I've done. Okay, in this case alpha was 1, beta was 1 in our example. Okay, all right, the next thing is we want to find the constant, so we multiply both sides by the common denominator. So we get a times s minus 1 squared plus 1 plus b times s minus 1 times s plus 1 plus c times s plus 1. So I'm multiplying everything by the common denominator. Now we'll set factors to 0. So let's set s to negative 1. So we get 1 on the left. Out here we get negative 1 times negative 1 minus 1 is negative 2. Negative 2 squared is 4. 4 plus 1 is 5. So I get 5a. Okay. And because we have negative 1 here, this will be 0, this will be 0. So this tells me that a is equal to 1/5. Okay, there's no more factors to set to 0, but I can at least set s to 1. Okay, and that'll help me find some of these other things. So we get 3. If s is 1, we get 1 minus 1 is 0, and we just get a. Plus out here, if you get s is 1, we get 1 minus 1 is 0, so b times 0 is 0. And out here we get 1 plus 1 is 2, so we get 2c. I know a from the top, so you can do some math over there and figure out c is going to be 5/2. So you need to plug that in here, and then you get c is 5/2. Now to find b, I'm going to compare terms. I'll compare the s squared term. There's no s squared term on the left, so we get 0. If you expand this, you'll get an s squared, so there's a plus b, because when you expand this, there'll be an s squared. There's no s squared there. Since I know a, b is going to be negative 1/5. So I got all my constants, so that's a great progress. So now what happens to 1? The 1 equation we started with, this guy here, remember we called it 1. It's a good idea to label things so you can see the flow. What does big Y of S become? On the right it'll be A over S plus 1, so it'll be 1/5 over S plus 1. Remember, this fraction is the same as this fraction because of the decomposition, so we just have to replace these guys on the top. Okay, that's what we are doing. So we get plus minus 1/5. We get S minus 1 divided by S minus 1 squared plus 1. The negative comes from this being negative, plus 7/5 times S minus 1 squared plus 1. So that is my decomposition. So we are still right here. Remember I said we solved for y and we did one extra step here. We did the partial fraction decomposition to make it easy to do this last step, the inverse step. So that's what we're going to do now. Now that we did the decomposition, we can do that inverse step. So I want to take inverse Laplace here. Okay. When you take inverse Laplace, remember Laplace of little y of t, I told you earlier, was what? Big Y of S. If I take inverses on both sides, these will negate each other. So what do we get? So the inverse Laplace of big Y of S is going to be what? Little y of t. So when I take the inverse Laplace of this guy, I should just end up with little y of t. Okay, so that's what we have. All right. Again, if I'm going too fast, just pause the video and copy and catch up. Okay. All right. So what do we do? This is what you guys did in section 7.4. Anytime you have 1 over S plus 1, Laplace of what gives you that? If you recall, Laplace of e to the at does, where a would be this number. You know, in this case, it's negative 1. So we get 1/5 e to the negative t. Okay. Minus, I'll pull that 1/5 out. If you recall, Laplace of what gives you that? If you didn't have that S minus 1, you would have what? Just S. Instead of S minus 1, if I had S, I'd have what? S squared plus 1. So this is cosine of whatever this is. This should normally is b squared, but in this case it's 1. So we get just t. Okay. But because these guys were shifted, we have to introduce that e. So in this case, we get e to the t cosine of t. Same thing will happen here. We get 7/5. We get e to the t sine of t. And there's your answer. Okay, this is really cool. If you notice, we found the homogeneous. Let me point out the solution so you guys can see. Okay, these two terms at the end are your homogeneous solution. Plus out here, this term here is your particular solution. Okay, so we found both the homogeneous and the particular solution, and we also found the constants C1 and C2. So everything came out nice. Okay, so that's a really nice feature of Laplace transforms. Not only does it give you both the solutions, homogeneous and particular solution, but it also gives you the constants that we would normally have to find using the initial conditions all in one chunk. Okay, so it's pretty cool. All right, let's do one more problem. So if you go back and look at it, the only difficulty solving Laplace transform is what? Doing partial fraction decomposition, and that's algebra. So that's all you're doing. Okay, so let's take a look at another example. So let's say if I have y double prime plus y is equal to sine of 2t. Okay, they've given us some initial condition. Y of 0 is equal to 2 and y prime of 0 is equal to 1. Okay, all right, so let's take a look at it. So the last time I went through all the detailed steps, right? I showed you how we took Laplace transforms on both sides and did that. I'm going to skip a few steps out here. So the first thing I'm going to do is take Laplace transform, and I just want you to do this and just show it. Just put that squiggly L so I know that's what you're doing. Y double prime is going to be what? S squared times big Y minus S times Y of 0 minus Y prime of 0 plus Laplace of Y is just big Y is equal to Laplace of sine is of 2t. Remember, Laplace of sine of bt is b over s squared plus b squared. That's what it is. Out here b is 2. So we get 2 over s squared plus 4. So that's what you're going to end up with. Okay. So now this time things are going to get a little ugly. It's nice when the initial conditions are 0. It makes your life easier. But in this case, they are not. This is going to be a 2. This is going to be a 1. So let's use those. So we get s squared times big Y. Okay. Actually, remember our goal is what? So we at this step. So we want to solve for big Y. Okay. So let's do that. I'm just going to do that quickly. So this term has a big Y in it. This has a big Y in it. So I'm going to pull that big Y out. Like I said, I'm just going to skip a few steps now. And then on the right we have 2 over s squared plus 4. And then these terms, this term which is going to be negative 2s will go to the right, so it'll become positive 2s. And this minus 1 will go to the right and become plus 1. Okay, so keep that in mind. We just move things over. The next thing we're going to do is divide everything by this. Now here's a thing. In the last example out here, I combined everything here. Okay, before I divided by this, if you look at that, I combined them. Sometimes it's advantageous to combine. Sometimes if you can see a couple steps ahead, it's smarter not to combine. So in this case, you might be tempted to find the common denominator here and combine all of these. But you notice that, let me do the next step and I'll tell you why it makes no sense to combine here. We get s squared plus 4 times s squared plus 1 plus 2s over s squared plus 1 plus 1 over s squared plus 1. We already know the inverse Laplaces of this, because if you think about it, this is sine of t, this is cosine of t. We already know them, so why combine them and undo all of that later by doing the partial fraction decomposition? So if you can see ahead and recognize that we already know the inverse Laplace of this, so don't combine them. All we need to do now is do the partial fraction decomposition for just this piece, because we already know both of the inverses for this. Okay, so let me call this 1 again, just like I did before. Okay, so now we're going to do the decomposition for just that piece that I've highlighted. So let's do that. 2 over s squared plus 4 and s squared plus 1. Now these are purely complex quadratics. Okay, now they're purely complex, so the way we break them, if you recall, is we would normally write it as as plus b over s squared plus 4, but it's better to split up the numerator right away, so that's what I'm going to do. So I'm going to get as over s squared plus 4 plus b over s squared plus 4. That takes care of this guy. Same thing for the next one. So we get cs over s squared plus 1 plus d over s squared plus 1. If I were to multiply these two, I would get s to the 4, so I should have 4 constants of integration. Now we're going to multiply everything by the common denominator. So we get s times s squared plus 1, as times that, plus b times s squared plus 1, because when you multiply by the common denominator here, the s squared plus 4s would cancel. We get cs times s squared plus 4 plus d times s squared plus 4. Okay, now that we have that, how do I find those constants? Well, there's not a whole bunch of things to set to 0. None of these are 0. But keep in mind what I told you when I did 7.4. Sometimes it's advantageous to compare terms, or you could also set s to whatever you want. You can set to s to any value, provided you do it on both sides. It's perfectly legal to do that. Okay, but for now I'm going to go ahead just to show you that. Let's set s to 0. So out here on the left I get 2. Anywhere you see an S, this is gone. Here, the A and C are gone, so you just get B plus 4D. That's pretty nice, because what does that tell me? B is equal to what? 2 minus 4D. So as soon as you find D, you'll know B. So that's nice to do that. I could also go ahead and set S is equal to 1, S is equal to 2, and get a whole bunch of equations and do it that way too. So sometimes, anytime you have a 0 and you can exploit that, I will do that. But usually I will end up comparing terms if you cannot set anything to 0. So let's compare terms. So I'm going to compare the S cubed term. There isn't one on the left. If you distribute A, you get S cubed, so you get A. If I distribute, S cubed, out here I'll get C plus C. So what does that tell me? A is equal to minus C. So that's also nice. So you're pretty much done. All I now need to concentrate on is D and C, and I'm done. Okay, so let's compare the S squared term. Okay. All right. No S squared term on the left. On the right, if you distribute, you're not going to get S squared. Out here we'll get B. Out here, when we distribute this, we're not going to get S squared, plus we'll get D. Well, that's nice, because we know from here, what do we know? We know that D is equal to minus B. Okay, so that's nice. So what does that tell me? Okay, if I were to combine, look at this equation and this equation, I should be able to do some work, the ones I have pointed here. I should be able to do some work and find B and D. Since D is equal to minus B, okay, I can replace this D with negative B. Okay, so let's do that. So we get B is equal to 2 minus plus 4B, since D is equal to negative B. I'll rearrange this, so I get negative 3B is equal to 2, so B is equal to negative 2/3. As soon as you know that, because of this relationship, this tells me what? D is equal to 2/3. Because it's negative B, this B is already negative here. Okay, so we got B and D done. The only thing left is to do A and C, so let's compare S term. On the left, again, I don't have any. When I distribute here, I'll get A. When I distribute it, I won't get anything, plus I get 4C. Okay, from here, so that tells me what? You can solve it many different ways. That tells me A is equal to negative 4C. So if you look at these two equations now, I can solve for C and A. So let's do that. So from those two, A is equal to negative 4C, so we get negative 4C is equal to negative C. Okay, so that tells me negative 3C is equal to 0, so C is equal to 0. Okay, if C is 0, what is A then? This would also imply A is equal to 0. So that's cool. We got nice value. So what does 1 become? 1 was this whole thing. We found this was the same as this decomposition. The only thing is A is 0 and C is 0, so these terms are gone. So you just get this. We know B and D, so let's plug those in. So big Y becomes B is negative 2/3 over S squared plus 4. That was B plus 2/3 over S squared plus 1, plus we had 2s over S squared plus 1 plus 1 over S squared plus 1. This was what 1 was. Now all we have to do is take inverse Laplace and we are done. So let's do that. Again, make sure you guys show that what we are doing. So big Y becomes little y of t. This, if you recall, anytime you have S squared plus 4 in the denominator, S squared plus something in the denominator, that's going to be either sine or cosine depending on what's on the top. If you have S on the top, it's going to be cosine. If you have a number on the top, it's going to be sine. So in this case, since we have number on the top, it's going to be sine. So let's do that. So to be a sine though, to be sine, keep in mind what has to happen. if you have s squared plus 4, I need a 2 for this to be sine of 2t. So I need to introduce a 2, or I have that 2 already present here, so I can just take that 1/3 out, and you'll end up with 2 over s squared plus 4, so that'll give you sine of 2t. Plus, out here, if this was a 1, then I would need a 1 on the top to be just sine t. So I can just take that 2/3 out, that'll become a 1 then. If I pull it out, then you'll just get sine of t. Okay. Plus, this will give you 2 cosine of t. This will give you plus sine t. Okay. Technically, this is not a very good answer, and why is that? Because we should really combine these two to get 5/3. Okay, so make sure you guys do that. So let me actually write it correctly and not box this. So we get y of t is equal to 5/3 sine of t plus 2 cosine of t plus minus 1/3 sine of 2t. Just for your own information, this is my homogeneous solution, and this is my particular solution. And we also found those the constants that we have in the front of the homogeneous solution, C1 and C2. Alright, so I've done about 2 examples for you. Let me do one other example that's interesting, and I'll explain why. So let's see if I give you this one. We have y double prime minus y is equal to t minus 2. They've told us that y of 2 is equal to 3 and y prime of 2 is equal to 0. So what's special about this equation? The special thing is the initial condition are given at 2. Okay, if you look at it, the initial condition when we do Laplace transforms, we always want an initial condition where at 0, because the form y double prime when we take Laplace transform ends up with y of 0 and y prime of 0. We don't want 2 here. There's no 2 here. It's actually 0. So there is a problem here that we need to fix. Okay. So what do we need to do? So let me write down a note first. Maybe that'll remind you in the future. Note the initial conditions aren't given at t is equal to 0. So what do we need to do? So we need to translate the initial value problem or the initial conditions at t is equal to 2 to t is equal to 0. So that's what we need to do. So let's take a look at it just graphically what's going on. Here is t is equal to 0 and here is t is equal to 2. So I want to translate this here, move this here. So if you recall from algebra, whenever we do an horizontal shift, out here we're doing the horizontal shift. Whenever we do a horizontal shift, it's always in the opposite direction of the sign. So if I write t plus 2, that means we're going to go 2 units to the left. So out here what we want to do is we want to change every t to t plus 2. So that'll help us shift it to the left is what we want to do. Alright, so let's take a look at that, how we go about doing that. Okay, so I'm going to do that. So what does my ODE become? Just the ODE, not the initial condition, just the ODE. Well, I had what? Y double prime. Remember, we're going to change every t to what? T plus 2. So we get y double prime of t plus 2. Okay. Then we had minus y of t plus 2. Because normally we don't write the t, but technically this is y double prime of t and this is y of t, just so you guys know. I'm going to have to change this to t plus 2. So we get t plus 2 minus 2, so those would cancel. Okay, so I'm just going to move this a little bit so I have room on the right. Alright, so that's what we have. So we end up with here, we end up with y double prime of t plus 2 minus y of t plus 2 is equal to t. Right. So now we're going to do a substitution. We're going to go let x of t equal to y of t plus 2. So if I take derivatives, the first derivative, I get y prime with respect to t. And when I take the derivative of the inside, we just get 1. So it's just, if I take the second derivative on both sides, I get y double prime. And when I do chain rule and take the derivative of the inside, I get 1. So that means I can replace y double prime with x double prime. So I get x double prime of t now. And y of t plus 2 can be replaced with x of t is equal to t. So that's nice because my ODE now became this. Okay, so this is my new ODE. Just keep that in mind. This is what we're going to solve in a second. But let's worry about the initial conditions now. What were my initial conditions? They told us that y of 2 was 3. That's what they had given us. So how can I use that? Well, let's take a look at the substitution we did. We know that x of t, okay, is equal to y of t plus 2. Now, what are we doing? Our original problem was a problem of y, and we had initial conditions in y. Our new problem is a problem of x, so we need initial conditions in x. So we want them at 0, so I'm going to set t to 0. So we get what? X of 0 is equal to y of 0 plus 2, which would just be y of 2, which is what? 3. So now I know x of 0 is going to be 3. So I have a new initial condition at 0. Okay. Similarly, I can do y prime of 2 was 0. So we get x prime of t. If you go back and look at it over here, what is x prime of t? It's right here. It's going to be y prime of t plus 2. So what is x prime of 0? Why are we finding it at 0? Because x is going to be a new differential equation, and we want the initial conditions to be at 0. So we're setting t to 0. We get y of 0 plus 2, which will give me y prime of 2, which is 0. So here's my new initial value problem that we are going to solve. It's going to be x double prime minus x is equal to t, and we get x of 0 is equal to 3, and x prime of 0 is equal to 0. So that's how we translate a problem. Once we translate it, the rest is just solving this using Laplace transform. So let me go through this so you can see one more problem. So Laplace transform of x double prime is going to be it's going to be s times big X minus s squared, minus s times x of 0 minus x prime of 0 minus the Laplace transform of little x is big X, and Laplace transform of t is 1 over s. That's from section 7.2. Okay. Oh, of t, sorry, I thought it was 1. If it's t, it's 1 over s squared. Now we know this is 0 and this is 3. Now I want to solve for big X now instead of y. I have s squared minus 1. I'm combining these two terms, taking a big X out, is equal to 1 over s squared. I'm going to move this term to the other side. It's negative s times 3, so it's negative 3s, so it'll become a positive 3s. And this is 0, so we're done. I'm going to divide both sides by what I have in parentheses. I get 1 over, okay, actually this time you can see that, let me just write it, please don't write this for a second. I'll get this plus 3s over s squared minus 1. If this was a plus, this would be cosine, but it's not. So this is not going to help. So I'm going to have to do partial fraction decomposition for this. I'm going to have to do partial fraction decomposition for this. When you have to do it twice like that, it's better to combine this into a common denominator and do that. That's what I meant earlier when I said sometimes it's if you can see ahead, it's better to combine, and sometimes it's not. So I'm going to find the common denominator here first. So you get 1 plus 3s cubed over s squared times s squared minus 1. So I found the common denominator here, which would be 1 plus 3s cubed over s squared. Then I divided by this to end up with this. Now, just for the sake of time, I'm not going to do the decomposition here, but you guys know how to do this. So if I were to do the partial fraction decomposition, okay, I did this earlier, so we get x is equal to minus 1 over s squared plus 1 over s plus 1 plus 2 over s minus 1. So that's what you're going to end up with. So now we're going to take the inverse Laplace of this. The inverse Laplace of big X is little x of t. This is just negative t. This is plus e to the negative t plus 2e to the t. Okay, that's what we get. But this is not the answer. Why is this not the answer? Because our original problem was a problem in x. We just solve, problem in y. We just solve for x. We want to solve for y. So what was y? So let's write that down. Since y of t plus 2 is equal to xt, we'll have to do another shift out here, right? We'll have to change t to what? T minus 2, sort of. So we get y of t will become what? X of t minus 2. So to find y in this function x, I'm going to change every t to t minus 2. Basically, I'm shifting, going back from 0 to this. Since I'm shifting to the right, we change t to what? T minus 2, because when we do a horizontal shift, it's opposite of the sign, you know. So that's all we're doing. So we end up with y of t. This is y of t is equal to x of t minus 2. Change this to t minus 2. So all of these t's will become t minus 2. So we get negative t minus 2 plus e to the negative t minus 2 plus 2e to the t minus 2. And that's how we have the answer. So sometimes it is important that you realize that if the initial conditions are not given at 0, to translate it to 0 and then solve the problem like you normally do. Now, one of the other cool things that we can do with Laplace transforms, and I do apologize, I should have listed that at the very beginning. Okay, one of the other things we can do with Laplace transform is solve variable coefficient problems. Remember, in chapter 4, we solved one particular type of variable coefficient problem, but now we can also solve other types. The one particular type that we solved in chapter 4 was the Cauchy-Euler. It was very specific. It was what? A times x squared y double prime plus b times x y prime plus c is equal to some forcing function, you know. The key thing was what? If you had two derivatives, we needed a square here. If you had one derivative, we needed an x here. So that was a very specific problem. But now we'll be able to solve other class of variable coefficient problems using Laplace transforms. So let's take a look at that. Okay, what is this section? C. So let's start with variable coefficient problems. Now we're not going to be able to solve a whole bunch of variable coefficient problems, but the particular class of variable coefficient problems we can solve using Laplace transform. So that's pretty cool. But to do that, we're going to need some special Laplace transforms. Okay, so before we can actually do that, we're going to need some special Laplace transforms. Okay, to do this, we need to find some special Laplace transforms, okay, that we haven't done yet. Okay, we know like Laplace transform of y double prime, we know Laplace transform of y prime, we know Laplace transform of e to the t, and so on. We know a lot of them, but there's some other ones we don't know that we need to find. But before I do that, let me also remind you of one Laplace transform that we're going to utilize here in a second. It is this one, the Laplace transform of t to the n of f of t. If you take a function f of t and multiply it by t to the n, it was what? -1 to the n times the derivative, not just any derivative, the nth derivative of big F of s, where big F of s is a Laplace transform of little f of t. Okay, so we're going to exploit this to find some new Laplace transforms that we're going to need to solve variable coefficient problems. Okay, because you can see there's a variable here, and let me show you what I mean by that. So let's take a look at the very first one we're going to do. So for the first one, we're going to go let n is equal to 1 and f of t is equal to y prime in this expression that I just wrote down. In this expression, we're going to do that. So what do we get? We get Laplace transform of t times y prime, because f of t is y prime, is equal to -1 times d over ds, okay, times what? Big F of s. What does that mean? Let's take a look at it. What is big F of s? What's another way to write big F of s? Isn't that just a Laplace transform of little f of t? Do you guys agree? This notation. So couldn't we write this, since f of t is y prime, so won't this be Laplace transform of just y prime? So that's what we get, Laplace transform of y prime. Okay. Well, that's nice, because we do know the Laplace transform of y prime, don't we? That's something we learned in section 7.3. So let's write down. We get d over ds times, we get s times big Y minus y of 0. That is the Laplace transform of y prime. Now we're going to distribute and take derivatives here. But the only thing is, remember, big Y is a function of s. Don't forget that. So out here we'll have to use product rule when we take the derivative. And y of 0, remember, y of 0 is my initial condition. It's always equal to some number, right? So it's a constant. So when you take the derivative of that, you're just going to get 0. So we'll end up with -1 times, when you do product rule here, you get big Y minus s times big Y prime. And then remember, y of 0 is just going to be 0 since it's a number. When you take derivative of a number, we just get 0. So that's what we end up with. So that, if you distribute the negative, will gives us a new Laplace transform. It is the Laplace transform of t times y prime is negative big Y minus s times y prime. Okay. That's really cool, because why is that cool? Because now it's a variable coefficient term involved here. Okay, so now if I have a problem like this, if I have y double prime minus t times y prime plus y is equal to 2. When I take Laplace transform of this, I know how to do this. It's s squared times big Y, s of y of 0 minus y prime of 0 minus. Do I know how to take the Laplace of this? Sure, I know, it's right here. That's what will go here now. Okay, so that's the advantages of doing that. So because that becomes variable coefficient, now we have a t in front of those y terms in the ODE. Let's take a look at another one. What if we let n equal to 1 and we let f of t equal to y double prime this time? Okay, so what do we get in that stored property of Laplace transform that I did over here, this property? I'm going to replace n with 1, f with y double prime, so you get t times y double prime is equal to negative d over ds, okay, times big F. But what is big F? Well, if I think about it, Laplace transform of f of t is equal to big F, right, notation wise, But what is f of t in our case? It's y double prime. So big F is just Laplace transform of y double prime. But we do know the Laplace transform of y double prime. What is it? It is s squared times big Y minus y of 0 s times y of 0 minus y prime of 0. So now we'll have to take derivatives term by term. The only thing is when we do the derivative of this, we'll have to use product rule. So we get 2s times big Y plus s squared times big Y prime. Okay. Out here, remember, this is just a number. Remember, initial conditions are basically at some number, right? Same thing over here. This is a number. So when we take derivatives, we just take derivative of s here, which is 1. So you just get y of 0. And out here, the derivative of a number is 0. So we don't even get anything. So it gives us this really nice property, Laplace transform of t y double prime. I'll distribute the negative over here. Okay. And I'll rearrange it so the s squares in the front. So you get negative s squared y prime minus 2sy plus y of 0. So there's your next one. So you can keep doing this. There's no end to this. You just look at different combinations. Let me do one more and then I will be done with that. Okay. So in this one, I'm going to set n is equal to 2. So we're going to go let n is equal to 2 and f of t is equal to y prime. So what do we get? We get Laplace of t squared y prime is going to be negative 1 squared will just become 1. And then we get d squared over ds squared of f big F. Big F is just going to be the Laplace of y prime. Okay, so that's what big F is going to be. All right, I do know that, so let's do that. What do we get here? We get, by the way, the reason why there's no negative 1, like I said, n is 2, so this is 2, so that's why it becomes just a positive 1. Okay, so we get d squared ds squared. What is Laplace of y prime? It's s times big Y minus y of 0. That's what it is. Okay. All right. So let's see, what do we get here? Let's go ahead and take the derivative. We'll have to use what? Product rule. So I have to take second derivative. So we'll start by taking the first derivative. So I'll write d over ds, and that'll give us big Y minus plus s times y prime. This will just give us 0 because that's just a number. Y of 0 is a number, you know. So that gave us the first derivative. Let's do the second derivative. We get y prime plus product rule here again. So we get y prime plus s times y double prime. So if you combine some of these terms, so we get Laplace of t squared y prime is equal to s times y double prime plus 2 times y prime. Okay, so that's another nice one that we should know. And the last one, I think I'm going to give it to you guys for homework, so you guys should know that. If I were to ask you to do this on the test or something, you should absolutely know how to do that. We're going to go let n is equal to 2 and f of t is equal to y double prime. Okay, so if you went through the same steps like I did for 1, 2, and 3 a minute ago, you'll end up with this. So Laplace transform of t squared y double prime is equal to, okay, we end up with s squared times y double prime, okay, plus 4s times y big Y prime plus 2 times big Y. So that's what this is. So you should practice to see if you can get that using n is equal to 2 and y f of t is equal to y double prime. So now we did these special Laplace transforms. Let me just do 2 quick examples on this and we'll be done with this section. Okay, so let's start with y double prime plus t times y prime. minus y is equal to 0. So this is a homogeneous problem, but it is variable coefficient, so that's special about this. They've told us that y of 0 is 0 and y prime of 0 is equal to 3. Okay, so let's see if we can solve this. So let's start by taking Laplace transforms on both sides. Y double prime is going to be s squared times big Y minus s times y of 0 minus y prime of 0. That's y double prime. What is Laplace transform of t times y prime? Let's go up and look at it. Where is that? That's right here. It is t times y prime. So you get negative y minus s times y prime. So we get negative big Y minus s times big Y prime. Minus y. What is Laplace transform of y? It's big Y. And Laplace transform of 0 is just 0. Alright. Normally, when we did the other problems, the next step would have been to solve for big Y. But wait a minute, I have y prime also involved, big Y prime involved. So let's rearrange this. So I get big Y prime. And then let's pull a y prime out from everything else. I'm sorry, big Y out. So there's a big Y here, and here, and here. These two can be combined, will be negative 2 big Y. So we get s squared minus 2. Okay. This is 0, and this is 3. So we get minus 3, which will go to the right hand side and become a positive 3. Okay. So that's what we have so far. Now, what are we going to do? Let's divide everything by negative s here. So we get big Y prime plus, okay, we get s minus 2 over, or we're going to divide by negative s. So let's flip these. So we get 2 minus 2 over s minus s times big Y. I flip these is because I'm dividing by negative s, and this will become negative 3 over s. Now this is a first order ODE, okay, in big Y and s. We can use integrating factor method that we did in chapter 2. Okay, so let's quickly do that. So to do the integrating factor, we called it mu, if you recall that, the mu, the integrating factor was mu, and we ended up with what? In this case, it'll be the integral of, so what do we end up with for this over here? We get e to the integral of 2 over s minus s ds. So we get e to the 2 ln of s minus s squared over 2. So this will give us s squared times e to the minus s squared over 2. Okay. So that's what we end up with, right? And then if you recall, the solution was what? It was y, little y or big Y in this case, 1 over the integrating factor. So we get s squared times e to the negative s squared over 2 times the integral g, which in our case is negative 3 over s, times the integrating factor s squared times e to the negative s squared over 2 ds, plus some constant time divided by the integrating factor s squared times e to the negative s squared over 2. Okay, that's what we end up with. Okay, so what do we get? Let's work our way through it. Okay, out here one of these s's will cancel. This is a simple u substitution for negative s squared over 2. You'll get a negative 2s in the bottom. So that'll give us, let's see, we get big Y is 1 over s squared e to the negative s squared over 2. If I do a substitution, if you do the derivative, you get 2s over 2. The 2's will cancel, so you'll get a negative s on the bottom, which will cancel this s here. And this negative will become a positive, so you'll get 3 times the integral of e to the u du. And out here we get plus, I'll just move this exponent to the top here. Okay. All right. And then we can integrate that. We get 1 over s squared e to the negative s squared over 2 times 3u is that, e to the negative s squared over 2 plus this. These will cancel. So we get 3s squared plus c e to the, this should be positive, I'm sorry, because when you move this to the top, this negative exponent will become positive. So that's what we get. Now here is the kicker. Now I'm going to do inverse Laplace, but before I do that, I want you to remember one very important thing. Okay, there was a property that I gave you in section 7.3, you can look at it, which stated that if you take the limit, this is, let me put a note and do this note. If you take the limit as s goes to infinite of big Y, you should always get 0. Let's take a look at this over here. Okay, if I take the limit of this as s goes to infinite, if x goes to infinite, this will go to infinite, this whole thing will go to 0, so that's good. This was a property, this always has to happen. This was in section 7.3. You can definitely go back and look in your notes. Okay, all right, but what happens over here? If I take the limit as s goes to infinite, you have e to the infinite squared over 2, so that's e to the infinite, which is infinite over infinite. If you did L'Hopital's rule out here, you'll end up with c e to the s squared over 2 times 2 just s over 2s. The s's will cancel, but this is still what? Infinite, as s goes to infinite. Do you guys follow? So we can't have that. We always want the limit of this to be 0. That is one of the properties of Laplace of the inverse Laplace of the Laplace transform. So what should we do here? Okay, so we can write out, since we want the limit as s goes to infinite of big Y to be 0, this would imply that we would have to take c to be 0, because we can't have this term present. If this term is present, then it'll go to infinite when s goes to infinite, and we don't want that. We want everything to go to 0. So we got forced to take c to be 0. So my big Y becomes what now? 3 over s squared. So we're just using this property of Laplace transform to recognize that we are forced to take c to be 0. Now that we have that, we can take inverse Laplace on both sides. So big Y becomes little y of t, and this just becomes 3t. There's your solution. Okay, so that was a nice interesting problem. We solved a variable coefficient problem using Laplace transform. So this is a nice trick to remember. You don't always end up using it, but it is a trick to remember. Okay, all right, let's do one more variable coefficient problem, and this will be a last problem in this section. We get t times y double prime minus t times y prime plus y is equal to 2. They've given us y of 0 is 2 and y prime of 0 is negative 1. Okay, first thing I'm going to do is take Laplace transform. By the way, this is not Cauchy-Euler. If this was a t squared, it would be Cauchy-Euler, but right now it's not Cauchy-Euler. So what is t times y double prime? I did that for you. T times y double prime right here, it's all of this. Okay, so I'll use that. So we end up with negative s squared of big Y prime, okay, minus 2s times big Y plus y of 0. That's what that was. This also we just used a minute ago. It was right here. Okay, except we are going to multiply by a negative, so these negatives will all become positive because we are multiplying by a negative in here. So we'll just end up with plus s times y prime plus big Y from this is equal to 2 over s. That's a Laplace transform of 2. Alright, so let's see what we can extrapolate. Y of 0 is what? 2. We know that. Okay, so let's collect some terms. Let's collect the y prime terms. Actually, yeah, let's collect them. So we get y prime is equal to, we get negative s squared plus s, okay, plus, let's collect y terms. We get negative 2s plus 2 is equal to 2 over s. Okay, all right. Oh, and I forgot, please don't forget this. This needs to go to the right, so it'll become a negative 2. Okay, so that's what we have. All right. We're going to rearrange this and divide by stuff. Okay, I'm going to divide by all of this. So I get big Y prime plus big Y. I'll take a negative 2 out. I'll get s minus 1 here. And when I divide by this, I get negative s out. So I get s minus 1. When I take a negative s out here, is equal to, okay, out here if you find the common denominator, you'll end up with 2 minus 2s over s, and if you take a 2 out, a negative 2 out, so we get negative 2 is s minus 1 over s. So if you take a negative 2 out, you'll get s minus 1 over s. And then you're going to divide by this guy, or this guy here. They're the same. All I did is take a negative out, so I'll put a negative here. S squared times s minus 1. Alright, so that's all it ends up being. These will cancel, the negatives will cancel. Same here, the negatives will cancel, so you get 2 over s big Y is equal to 2 over s squared. That's what you end up with. This is again a first order ODE. ODE degree is 1. You can use the integrating factor method again. This time I'm not going to go through it, but if you wanted to find the integrating factor, it would be what? E to the integral of 2 over s ds, which will give you e to the 2 ln of s, which would give you s squared, which would be my integrating factor. And you can go through all the steps to do that. So if you did that, you'd end up with big Y of s is equal to 2 over s plus c over s squared. Now let's take a look at what I told you earlier. What did I tell you? We want the limit as s goes to infinite of y to be 0. Well, this will go to infinite, this will go to 0. This will go to infinite, this will go to 0. So it is going to 0. So is there a need to set c to 0 here? No, we don't have a need to set c to 0 because it is going to 0. If this term wasn't going to 0, then I would set c to 0 like I did in the previous problem. Okay, so I'm just going to go ahead and continue and take inverse Laplace. So I get y of t is equal to 2 plus ct. That is the inverse Laplace of that. How do I find c? If you recall, out here we only used one initial condition, this one. We still haven't used this one, so let's use that. To use that initial condition, I'll have to take the derivative. So let's do that. I get y prime of t is equal to c. So that tells me that y prime is equal to negative 1 when t is equal to 0. So we get negative 1 is equal to c. So what is my final solution here? Y of t is equal to 2 minus t. So that's how we solve initial value problems with Laplace transforms. That's what I've shown you how to do in this section and in this video. Okay.